So up to now we've been looking at horizontal projectiles going off the edge of a cliff, and we realized that when we had cases like this, the object had a trajectory like that. We could figure out the delta x by figuring out how long it was in the air, multiplying it by the horizontal velocity which was coming in. We made our t-charts, and we would always have VI equals 0. And delta y was whatever, negative h, and acceleration was negative 9.8. And we use that to go ahead and find the time, plug it in here, and go through that process. I'm afraid that was pretty clear for all of you, but now I want to show you what happens if we were to launch a projectile at an angle. So now I am going to say launch this projectile at, say, 30 meters per second at an angle of, say, 35 degrees. Well, now I can no longer say that my VI is going to be 0, because you see that we do have a y component and an x component to this velocity. So now we have both an x velocity and a y velocity. And so no longer is this VI going to be 0 up here. We are going to have that new value. But other than that, it really is a similar question. Not much changes. We know that this is going to have a trajectory something like this. We'd be interested in seeing how far it goes, and perhaps how high up it goes as well. That'd be the max. And so we make a similar t-chart. If you look at this, you see that Vx is going to be V times cosine of theta, and Vy would be V times sine of theta. And these are two numbers we can easily calculate when we know what V is, which would be 30 times cosine of 35 degrees, and that'd be 30 times sine of 35 degrees. And we can put this in our calculator to figure out what the values are, and there we have to use it. Now, go back and make our t-chart again the same way. And so again, remember, the only thing working here is simply velocity equals displacement over time, because there is an acceleration here. And then on the y side, of course, we have our kinematic equations, and we would use all of those. So starting with this, we see that Vx is V cosine theta, and Vy, which is your initial velocity, is V sine theta. I hope you can see the initial velocity, because that's the velocity with which we're launching it upwards. Acceleration is still negative 9.8, and our time is what we're going to look for. And of course, if we were to look at this motion, there's two ways of analyzing it. You could either analyze the entire motion in one shot, or you could say, hey, let me figure out how long it takes to get to the top, and then I'm going to multiply that by 2 to get the time it takes to get to the bottom. Now, you could do it both ways. I am going to do it where I treat it all as one motion, because my question that I'm going to be answering now is, how far does it travel? Okay, so that's a question I would like to be answering, for which I know I need to find my delta x. And that's going to be, delta x is just going to be V cosine theta times t, which is the horizontal velocity times the time. So all I need to do is find the time here, just like I did before. So what's my third condition? Previously, when you were looking at an object making it all the way to the top, we said Vf was going to equal to 0. Well, but in our case, obviously, our Vf is not going to be 0 when it comes down here. We're looking at the entire motion. So what other variable can you see in this entire motion that you can use? We either need to get a delta y in there, or we're not going to pretend we don't know that Vf is the same. So then, if you look, what happens to the displacement? The displacement starts from 0, goes up all the way to the maximum h, and then comes back to 0. Well, what do you know about an object that comes back to its starting point? What's the displacement for the entire journey? I hope you said 0. So delta y is 0. That's when it comes back in. And now all we're going to do is solve for time here, and then plug it in there. Okay, so part 2.